Hello and welcome to Grokking Graph Analytics and Algorithms. In this lesson, we're going to cover Dijkstra's algorithm. Recall, with breadth first search, we were exploring a friend network to see if we knew someone who had tickets to a concert. Breadth first search was useful since there's no cost in asking a friend, or the cost is constant. Suppose now you have a graph with a cost associated to each edge. So now every one of those hops has a cost associated with it. Dijkstra's algorithm can help us find the cheapest path in a graph. This path may have several cheap hops as opposed to a few hops that are more expensive, like breadth first search would find. Let's consider this map of an imaginary city. You see we've got major streets and some side streets. Let's say you're over here, and you want to get here. As you can see, there's several different routes, and some of the streets are wider and maybe nicely paved, and others are just short dirt paths. Some are shorter, some are longer. Each route has a cost associated with it. A simple heuristic we can use is to make cost a linear function of road length. Let's convert this map to a graph by treating the streets as edges and intersections as nodes. Why don't you pause the video for a moment and see if we can convert this map to a graph. Go ahead and pause the video and think about it for a minute. Okay, let's convert this graph to a map by treating the streets as edges and their intersections as nodes. This is similar to our maze problem from the depth first search section, only this time we're going to associate a cost to traveling on an edge. We'll make the initial cost analogous to the length of the road, but that cost may go up or down as the roads get more or less rugged. Perhaps you put a penalty on each road as a function of the speed limit, for example. Suppose you performed a breadth first search on this graph to get from the start to the end node. You could get to the end in 2 hops with a cost of 5. But if we take a minute to examine the entire graph, we could find a shorter route. Suppose instead of checking each route, you only consider the cheapest route at every step, and also track the cheapest route to a given node, updating it when you got new information. The general strategy of replacing solutions with better ones is known as relaxation. For example, a walk from A to the end costs 4, but if we could get to B cheaply, we could do it in 2. Dijkstra's algorithm helps us accomplish that. Let's see how. To implement Dijkstra's algorithm, we're going to keep track of our current node, and so that's S for now, the start, and we're also going to track the travel time to each node. And we also want to track the previous node that led to that node using the best travel time. Well, we have S, A, B, C, and our end node. And we don't know the travel time to anything except the start node, and that's 0. So we mark all the other start times as infinity. The next step of Dijkstra's algorithm is to look at all the neighbors of our current node and update their travel time as being the time to the current plus the edge length from the current. So the neighbors of S are A and C. And the time to go from S to A is 1. And the time to go from S to C is 2. So we can update A as having a travel time of 1 with the previous node of start, and we can update C as having a travel time of 2 with the previous node being start. We then mark the current node as visited, so I'm going to put a V right here. And we repeat this with the next cheapest unvisited node. Our next cheapest unvisited node is A. As you can see, it's got a cost of 1 versus C, which has a cost of 2. Then we get the list of its neighbors, which is B, and E. The travel time to B is the time from A to the end plus the travel time to A, which is 1. So the travel time to B so far is 2, with its previous node being A. Why don't you take a minute to pause the video and calculate the travel time to the end node going through A. The travel time from A to the end node is 4. And then we add the best travel time to A, which is 1. So the travel time to the end node becomes 5. And our previous node is A. We also have to mark A as visited. Let's go ahead and talk through the rest of the algorithm with this graph. The next cheapest unvisited node is B. So we mark that as our current. B's neighbors include A, C, and E, but we've already visited A, so let's not worry about that. The time from B to C is 1, and the time to B is 2, so the time to C is 3. And the time from B to E is 2, and the time to B is 2, so the total time is 4. Let's go ahead and update those times in our tables. Well, we see that we already have a path to C that only costs 2, so there's no need to update it. Now, if we look at our end node, we see that its current best cost is 5, but we found a path that has a cost of 4. So we update that. And we also update the previous node as B. We then mark B as visited and go to the next cheapest unvisited node, which is C. Why don't you take a minute to pause the video and see if you can complete this round of the algorithm. Okay, let's keep going. C's neighbors include the start and B, but both of those have been visited, so there's no need to keep going. We're going to mark C as visited, and we've reached the end node, and all of its neighbors have been visited. So we see that the best cost from the start node to the end node is 4. Dijkstra's algorithm is the most complex algorithm we've reviewed so far. I'll be sure to run through more examples in future videos. For now, let's consider the algorithm's implementation. At each step, we want to track the cheapest unvisited node. What does tracking the cheapest unvisited node at every step look like? Let's say we had objects with a cost associated with them. So we have something that costs, I don't know, like 5. Let's just say we have marbles with different costs on them. And we had some kind of bag that we could put them in any order. And every time we asked, it would give us the cheapest. So it would be 2, then 3, then 5, and then 6. Well, we do have a data structure that works similar to this, the priority queue. In Python, we can implement it quickly with a min heap. Let's go ahead and develop some pseudocode for Dijkstra's algorithm. We'll use our input G as a graph and a starting node S. Let's define n as the set of all nodes. And we'll need a distance map. And also a map of the previous node. Next, we're going to say the variable q is a min heap with all of our nodes in it. And now we can start our loop. First, we pop the minimum element, and that'll mark it as visited. Then we look at all of our current node's neighbors, and we create a temporary variable representing the distance from our current node to the neighbor. And now we can update our distance map. We also update the previous map. So that's the pseudocode for Dijkstra's algorithm. Dijkstra's algorithm is very useful in finding cheap routes in directed and undirected graphs with or without cycles. But one thing to look out for is negative weights. Dijkstra's algorithm fails here. Recall in Dijkstra's algorithm, once a vertex is marked closed, we assume the algorithm has found the shortest path to it. It won't have to revisit or redevelop that node again. It assumes the path developed is the shortest. But with negative weights, this might not be true. Starting Dijkstra's algorithm from A will first develop C, so it'll fail to find the path from A to B to C. To address this, we can use the Bellman-Ford algorithm. Let's go ahead and wrap up what we've covered today. Recall, breadth-first search was very useful with constant or zero cost in a graph. If you have a graph with cost associated with each edge, you can use Dijkstra's algorithm to find the lowest cost path. This may have more jumps, as breadth-first search would find, but each jump will sum up to a lower cost. Dijkstra's algorithm uses what's known as relaxation to continually improve the state of our solution. If you have a graph with weighted edges, such as a map or certain process maps that have costs associated with each process, you should consider using Dijkstra's algorithm to find the cheapest route through that graph. The pseudocode for Dijkstra's algorithm relies on a min heap to track the nodes that haven't been visited and to visit the cheapest node possible. Dijkstra's algorithm fails with negative weights. To address that, you can use Bellman-Ford.